All right, everyone. So we're going to go ahead and get started on the next section, section 4.4, linear approximation. So essentially, we pretty much established, and we kind of like briefly went over like a topic like this, where if we were to zoom in all the way into any point of a line, we can pretty much see that there is like local linearity within a function. Okay. So with that local linearity, that's essentially telling us that we can create a tangent line through a parabola like that. So what we can do is we can actually use this tangent line to come up with an approximation for something that's relatively close to that point that we found the tangent line for. So for example, let's say that this is the tangent line at x equals, let me just make up a number 2, right? And this is obviously a function f of x. So obviously f of 2 is going to be right there at that point of the tangent line. Well, what if I wanted to know what this value is at x equals 2.01, right? Well, first of all, 2.01, I mean, you could just, I know it doesn't look like it's going to be close in value, but let's just pretend that this is a very zoomed in version of the function. This x value of 2.1 will be a pretty close y value for x equals 2. Now, what we can do is we can actually, use our tangent line or our tangent line and plug in x equals 2.01 inside of our equation of the tangent line so that we can get sort of an approximation of what the actual value is. Now, obviously, this is the value you're going to end up with, and the true value, the exact value is there, right? This right here is just an approximation. And there's obviously going to be some kind of difference, and that's what we're going to be calculating here, the percent error of the approximation. Why is this necessary? I'm not 100% sure, but it is something that we have to learn. It is something that's in the calculus curriculum, so we're going to learn it. All right, so the first thing we got to do is the main thing is we got to figure out what our tangent line is. So obviously the first thing is we got to figure out what is the slope, find the slope of, now I'll just say, find the slope using the derivative, all right, you're going to find the slope of like the point that you're approximating nearby. And then the second thing is you got to create the equation of a tangent line. And then the last thing you're going to do is you're going to plug in that x value into the tangent line to get what the approximate value is of that function. So you're going to plug in the x value to be approximated. I don't even know if that's a word, but it makes sense to me. So hopefully it does to you. And then obviously, like I'm saying, your approximation isn't going to be what the exact value is. So if you want to know what is that percent error, this is the formula you have to use. You have to do the exact value minus the approximation, which is pretty much the difference between the two, divided by the exact value, and that'll give you the percent error. You probably have done percent error several times in other classes, and this is just sort of a continuation of that. So I'm going to start you off with some basic examples and then kind of get into, this is one of those sections that isn't going to take very long for you to do, and even the problem set is not that long. So hopefully it should make sense, and hopefully this video doesn't turn out to be too long. But for the first example, it says the function f is twice differentiable where f of 3 is equal to -2 and f prime of 3 is equal to 5. Write the equation of the tangent line, then use the equation to find the value of 3.1. So essentially here, you notice that the x value that we're finding the equation of the tangent line for is at x equals 3. And we're going to use that equation of the tangent line to approximate the value of f of 3.1. Okay, so obviously to create to create our tangent line equation, we need two things. We need our point, which we have right here, 3, -2. And we have our slope, right? Because the derivative at that point gives us the slope, which is 5. And we can just create our tangent line equation from this. So our tangent line is going to be y plus 2 is equal to our slope 5 times x minus 3. All right, so then as far as the approximation is concerned, we're just going to plug in, if we want to know what the approximate value of 3.1 is, what is the y value at that? We're just going to plug it into our tangent line equation. So y plus 2 is equal to 5 times 3.1 minus 3. So that's 0.1. 0.1 times 5 is 0.5. Minus 2, y is equal to negative 1.5. That's our answer. All right. So this is pretty simple. I mean, this is just kind of just building off of things that we've already known how to do. The hardest part is creating the tangent line equation. All right. So this is a really popular question that I've seen many times when it comes to this topic. So it says, consider y equals sine of x at x equals pi over 3. Since the angle pi over 3 is equal to 1.047197.5, let's write the linear approximation for x equals 0.05. So you'll notice 1.05 is really close to this. So if we find the equation of the tangent line at pi over 3, then that should give us a pretty close approximation. Same thing up here. 3.1 is pretty close to 3, so we can use the tangent line to give an approximation of what that value is. All right. Personally, I don't know why they don't just plug in the value into the original function, but again, I don't know. So we'll just go ahead and just do what they ask us to do. All right. So first of all, we can go ahead and decide what our point is. Our point is x is pi over 3. And then if I plugged in pi over 3 into this, the sine of pi over 3, that is the y value. So that's radical 3 over 2. Okay. And then our slope, well, for the slope, we actually have to derive this. So we know that y prime is equal to derivative of that is cosine of x. So then y prime at pi over 3 is equal to cosine of pi over 3, which is 1/2. So that's our slope. All right, so now we can create our tangent line. Our tangent line is, let's see, y minus radical 3 over 2 is equal to our slope, 1/2 times x minus our x value minus pi over 3. Okay, so then if we plugged in, they want us to approximate at 1.05, so our approximation will be, I'm just going to add the radical 3 over 2 to the answer. So y is equal to 1/2 times 1.05 minus pi over 3, and then plus radical 3 over 2. All right, so then if we plug in, so our y value ends up being, let me go ahead and calculate this. I don't have my graphing with me. So let's see, 0.5 times 1.05 minus pi divided by 3 parentheses plus radical 3 divided by 2. You get 0.8674227. All right. So that's our approximation. Now, the other thing they want us to do is figure out what the percent error is. So in order to use the percent error, there are two things we need. We need our approximation value, which we have, and we need to figure out what the exact value is. Okay, so let's figure out what the exact value is. So if I actually plugged in 1.05 directly into my equation, y is equal to sine of 1.05. Crap, I don't know how to check the mode for this. I hope it's in radians. We'll find out. So let's see, sine of 1.05, it should be something close. Nope, it's not in radian mode. I don't know how to convert it to radian mode. And I'm wasting time in this video. Well, maybe if I click on that. How do you switch this to radian mode? Okay, you know what? Let me go to my computer and calculate it. Sine of 1.05. There we go. So if I had a graphing calculator in radian mode, it would be 0.86742 now. Okay, so really there's only a difference of like 0.004, it looks like. So if I wanted to find the percent error, I just got to go ahead and put my exact value, so 0.867423 minus 0.867427 divided by the exact value again, 423. Take the absolute value of that, multiply it by 100%. So a lot of typing, but we'll get it done. 0.86 0.86743 minus 0.867427 divided by 0.867423 is that times 100%. And we're taking the absolute value, so it's ignore the negative. So that's equal to 0.00046%. Let's do 461 for 3 sig figs. Or I don't even know if that's even 3 sig figs, but whatever. I'm not a sig figs kind of guy. So yeah, there you go. That is the percent error. So I mean, you can tell that the approximation is pretty damn close with that. So let's go ahead and do the last example. I'll come back because I have to stop the video for a second, but I'll be right back. All right, so this last example is pretty much the last type of variation that you're going to see for this type of problem. So it says, for the function f prime of x is equal to 4x minus 1 and f of 1 is equal to negative 2 is concave up at x equals 1, what is the estimate for f of 1.2 using the local linear approximation of for f at x equals 1? Is it an underestimate or overestimate? So this last part is pretty much going to be you're going to be able to answer that based off of the information that it's concave up. But first, let's go ahead and do the linear approximation. So obviously, for the linear approximation, you need to figure out what the equation of the tangent line is. And obviously, for that, you need two different things. You need the point, and the point in this case is x equals 1 and y equals negative 2. You're also going to need to know the slope, which is given to you by f prime. So this is this is f prime, or the slope at any point for x for the function. F prime of 1. Let's see, if I plug in 1, 4 times 1, 3 minus 1, no, 4 minus 1 is 3. So that's going to go ahead and give you the slope. So now you just got to create your tangent line equation, and we should all be experts of that. So tangent line, we have y plus 2 is equal to 3 times x minus 1. All right, so now if we want to figure out what the estimate is of f of 1.2, we just got to plug in 1.2 into our equation and get our value for y. So I know that y is equal to 3 parentheses 1.2 minus 1, and then I subtract 2 on the other side. So then y is equal to 3 times 0.2 is 0.6. 0.6 minus 2 is negative 1.4. All right. So that gives us our approximation. Now, the other question that you have to understand is whether or not this is an overestimate or an underestimate. So the fact that it's concave up should pretty much give you the answer. So I'll just kind of go back to an older part of the notes. You'll notice that if the function is concave up, your tangent line is going to fall below what the actual value is going to be. All right, so your approximation is going to be an underestimate of what the exact value is. And it would be the opposite case. Like, I'll just draw a random example of if it was concave down. If it was concave down and you had your tangent line there, right? Whatever you, so let's say we're looking at an x value over here. This approximation is going to be above what the actual value is. So if it's concave down, your approximation is going to be an overestimate. And if it's concave up, right, like this one, then your approximation is going to be an underestimate. So the way I'm going to answer this question is I'm going to say, if the function is concave up for x equals 1, then our estimate is an underestimation of the exact value. Exact value for f of 1.2. All right, so that's pretty much it. This is the one section that's not gonna, it shouldn't take you too long to get through the problem set, and it's one of the shorter ones that we're gonna see in this section. It's nowhere near as heavy or complicated as the related rate section. So go ahead and get started on your problem set, and if you have any questions, you're more than welcome to send me a message or ask me, and that's about it. Take care.